And it looks like everybody can see my written sheets, so we will get there. So where we were before, we had issues on Wednesday. Last Friday, we got to the point that we had defined our 3 kinematics equations. And those were that my change in position was going to equal my initial velocity times time plus my acceleration divided by 2 times squared. That was my original change in position. I also have my velocity final is equal to my velocity initial plus acceleration times time. And I have velocity final squared is equal to my velocity initial squared plus 2 times my acceleration times my change in position. This one has variables x, t, and acceleration. This one has variables v, acceleration, and time. This one has variables velocity, acceleration, and x. Because one of the questions that we always get to is, I don't know when to use which equation. So let's look at a problem here. We have a horse travels 100 meters with an acceleration of, we're going to do 0.1, we're going to do 0.01 meters per second squared. What is the velocity of the horse if it starts with an initial velocity equal to 0? So we've got our problem here. We've been told we have a distance of 100 meters. So my change in position is going to be 100 meters. We've got an acceleration of 0.01 meters per second squared. And we're told the initial velocity is equal to 0. And we want to find our final velocity. So I'm going to look at my equations here. I don't have time, so that equation I'm not going to use. I don't have time, so that equation I'm not going to use. This one has all the variables that I need, so that's the equation that I'm going to use. So I'm going to write down my equation that I'm going to use. The final velocity is equal to my initial velocity plus 2 times my acceleration times my change in distance. My initial acceleration was 0. Or my initial velocity was 0. My acceleration is 0.01 meter per second squared. My change in position is 100 meters. I'm going to end up with meters squared seconds squared. And this is a velocity final squared. So that's going to end up being, I'm going to put in my calculator, 2 times 0.01 times 100. The horse would have been traveling at 2 meters squared seconds squared. I have to take the square root to solve for that. So I'm going to take the square root. So the horse is going to be traveling at 1.14 meters meters per second. So I can look at my problem to be able to determine which equation I want to use. Now, this was a simple problem, so we didn't necessarily draw it, but usually you want to draw your picture here. So there's my horse, and we're going to travel 100 meters, and we want to know the final velocity at the end. And typically on my exams, when you're given a problem, if you draw the picture, you're going to be able to get more points for that. Okay, so we've got our horse traveling. So that's one of the ways that you can tell what your equation is going to be. The other thing I would recommend is going through each of the examples in your text because they're very, very helpful. So what we're going to do next is we're going to start here. We're on a cliff. So I have a person is standing on a cliff. They are going to toss a ball with an initial velocity of 1 meter per second upwards. We're doing one-dimensional motion, but we're going to toss the ball at 1 meter per second upwards. Oh, actually, we're going to do a little better. Let's go ahead and say 10 meters per second upwards. We are going to start timing when the ball passes the edge of the cliff. We're going to start timing when the ball passes the edge of the cliff. T is going to equal 0.83 seconds when it hits the ground. We're going to find the distance from the top of the cliff to the ground. We're going to find the total time of flight. We're going to find the maximum distance the ball was above the ground. Okay, so I tried to write out the question so that you have the whole question there to work out. But what we're going to do, so what's intended here is we have our person. The person's going to toss the ball upward. The ball, let's see, I'm going to use a red pen here. The ball is going to travel like this. It's going to just miss the cliff. And this is our ground. So my ball is going to travel up there. Now, the problem doesn't give you everything that you need to know because it assumes that you know a couple of things. We have a vector. Vectors have direction and magnitude. So in this case, when my ball goes up and it comes back down, we know at this velocity at the top. We know the velocity at the top because I'm going to change direction. So the velocity at the top, which we're going to use as VT, has got to be equal to 0 meters per second. Because as I get to the top and I change direction, I got to go through 0. So this is one of the knowns not explicitly stated. It's one of the knowns not explicitly stated. All right, that's great. We got a known that's not explicitly stated. It works out really well. The other known that's not explicitly stated is that when I'm in the y direction on Earth, our acceleration is going to equal, the magnitude of our acceleration is going to equal to the magnitude of g, which is 9.81 meters per second squared. Okay, now if I say that up is positive, g is going to be minus 9.81 meters per second squared because it's acting downward. So we've got our motion going up and it's coming back down. We've got our vectors here. We've got our acceleration due to gravity. We've got our sign convention. And now we can write some things that we know from the problem. So we have our initial velocity was 10 meters per second. We know the time that it takes for it to fall is 0.83 meters per second. Now, a couple things that I'm going to show you, and as we're going to deal with this, we can use symmetry. And so there's a place that we can check some things. All right, there's a place that we can check some things. As this goes up and comes back down, at this point, if we assume that this velocity is from the edge here, we know that at this point, it's going to be traveling at a negative 10 meters per second. At that point, as it passes the edge of the, that. So we can do that. That is helpful for us. So I'm going to draw my picture over here and we're going to look at these items again. So if I have my lift, we've got the ball going up at 10 meters per second. When the ball travels down at this point, it's going a negative 10 meters per second. We've got our cliff. And now we know our time. And the first thing we want to find is this distance. And now we also know that gravity is a negative 9.81 meters per second squared. So I have a known initial velocity of minus 10 meters per second. I have a time that's 0.83 seconds. I have an acceleration is minus 9.81 meters per second. I need to know distance, which is going to be my change in y, which is my change in position. So the variables I have are v, a, t, Well, that's not a variable, that's known. And I have X. This is known. So there are my variables. So I can look at my equations. And if I go back here and I look at my equations, I have X, T, and A. So this is the one I'm going to want to use. My change in position, which is my change in Y, which is my distance, is going to be my initial velocity times time minus G over 2 times squared, because A is equal to minus G. So I'm going to have minus 10 meters per second times 0.83 seconds minus 9.81 meters per second squared, 0.83 seconds squared divided by 2. So I get negative 8.3 meters minus, getting out my calculator, I've got a negative 3.38 meters because my second squares cancel. I get a negative 11.8 meters. So the distance from the top of the cliff, so if I'm answering the question, if I'm answering that question, I'm going to say 11.8 meters because this tells us direction. So we're able to do that calculation to show what the direction is. So this is the distance to, so this gets us our first, this was our part A. Now we want to know the total time of flight. So this time I'm going to look at my picture a little differently. I'm going to use the same data, but I'm going to look at my picture a little differently. Because if I look at the time of flight, that's going to be the time that it takes to get to the top. So we're going to go up and down. So I've got the time there. I've got the time that it takes to fall. And then I have the time that it went down from the top of the cliff. So we know this part. And now I need the time that it takes to do that part. Now there's a couple ways I can do it. I can look at the time it takes to go from V initial equaling 10 meters per second to V final at 0 meters per second, where my acceleration is equal to minus 9.81 meters per second squared. And this would give me the time that it goes up. I can use that same one, the time from V initial is equal to 0, because that's at the top, to V final equaling minus 10 meters per second square or seconds, and using my acceleration as minus 9.81 meters per second squared. Or I can do time, and then these two I would have to add. I'd have to add those two because that's doing this time and it's doing that time. Or the time it takes from V0 is equal to 10 meters per second to V final is equal to minus 10 meters per second with my acceleration at minus 9.81. And that gives me this whole time. So we're going to do that one because I'm going to do it in one step. So now I have my V final is known. My acceleration is known. What's not known is my change in position, or my change in position is kind of known because it's 0 if I'm doing this one. Time is what I'm solving for. Time's what I'm solving for. So I can look at my equations again. So let's look at my equations. I know my velocity, I know my acceleration, I'm solving for time, so I'm going to use that one. So I get V final is equal to V initial plus my acceleration times time. So I could use that equation. So my V final is minus 10 meters per second. My V initial is 10 meters per second. And my gravity is minus 9.81 meters per second squared, and that times time. So I could do it that way, but I can also do it with my variables beforehand so I can punch it into the calculator easier. So I'm going to get my velocity final minus my velocity initial is equal to acceleration times time. Time is going to equal velocity final minus velocity initial divided by my acceleration. So now I'm going to get minus 10 meters per second divided by minus 9.81 meters per second squared. I end up in seconds, which is what I want to do. Okay, end up in seconds, what I want to do. So I get minus 20 divided by minus 9.81. And I'm going to total time of travel, or total time is 2.3 or 2.04 seconds. But that's the time, that's the time it takes to go from here to here. So that total time was equal to 2.04 seconds, but it wanted total time of flight. And that's going to be, adding those is going to be 2.87 seconds. So that's what I would end up putting in as my answer in WebAssign for that particular problem. So keys here are, I wanted to show you there's more than one way to come up with the solution. There's more than one way to come up with that solution for this particular one, and I showed you a couple of different ways to do it. So let's do the last one. Going to look at the problem a little differently. This time the question was asking, so our ball goes up like this and comes down. This time the question was asking, what's this distance? We want to know that distance. Well, at the top, we know our initial velocity is going to equal 10, or no, sorry, my initial velocity is going to equal 0 meters per second at the top. We also know one of the things is this one, by doing this, we might need this time, but we can figure that time out. That time is going to be 1.02 seconds. You can do that two ways. One is we found what the total time was, or we can go ahead and solve it for this. If we solve it for this, we're going to get the 1.02 seconds. So we know the total time it takes to fall. The maximum distance. The time it takes to fall, the maximum distance is 1.85 seconds, because I'm adding the 1.02 to the 0.83. So you get that total time it falls. And we know, so if I want to do my change in distance, that's going to equal my initial velocity times time minus gravity divided by 2 times time squared. We know that. We know gravity. We know time. Change in distance is what I want. This is going to be 0 times my time. It's going to equal or minus 9.81 meters per second squared. Divided by 2 times squared is 1.85 seconds squared. I'm going to get 16.8 minus 16.8 meters is the total distance that it fell. Let's say I want to know the final velocity down here when it hits. We can determine that too. The final is equal to my V initial plus my acceleration times time, which in this case is going to be V initial minus gravity times time, which is going to be 0 meters per second minus 9.81 meters per second squared divided by 2 times my 1.85 seconds. I'm going to end up with a negative value because my velocity is going down, so I should have a negative value. Oops. I'm going to go negative. That number's not right. We got negative 0.07 meters per second, and that number is not correct. And now the question is, how do I know that number is not correct? Because we know at this point, this should be a negative 10 meters per second. So I should have something greater than 10 meters per second. Let's go ahead, and something's not right here. Let's do my initial velocity of my minus 10 meters per second minus my 9.0. I divided by 2. There's no 2 there. I did something totally wrong. But that's how you check to find out if your answer is correct. That answer was not correct because we knew at this point that it was minus 10 meters per second. I threw in a 2 for no apparent reason. All right, I threw in a 2 for no apparent reason because it's not in my equation. It's in this equation, but it's not in that equation. So I did something incorrect, but that's how I knew I did something that was incorrect, because I used some knowledge about my problem. So we'll try this again. 1.85 seconds. Try that again. Much better. I get minus 18.1 meters per second, not second squared. So make sure my units work out. So that shows you that it's easy to throw in an extra factor that you weren't even thinking about. So that's one issue that you have. It also shows you how you can verify and check for how you're making or you made an error. So that's one thing that you can do. And so that really does help us. So this problem, there's lots of things you can do with this problem. We're all working in one-dimensional motion. We were working in the Y direction. So I did have an acceleration that I had to work with. I was able to use a variety of equations. There's more than one way to get to the answer when you're working with these kinematic equations. And showed you that, you can make a mistake and you can catch your mistake before you get too far. Drawing your picture helps. Knowing where you're drawing your picture and how you're doing that really, really helps. So rather than starting another problem, because the next problem I want to do is a little more complicated, but this one gets you a whole lot of different things that are there. It should get you enough information to be getting your homework started for chapter 2. If you have questions, I will be at my computer this weekend, so I will be working on stuff. So you want to go ahead and do that, but I am tied up most of the day. And Taryn, if you're still on, I want to chat with you for a second because I'm trying to figure out your question that you had asked me. So I want to get that one done. But for everybody else, unless you've got a question, you guys can take off. And we'll see you on Monday.